All right, y'all, I'm gonna go ahead and start with today's stuff. Now, hopefully you wrote those problems down. We're gonna come back to them in a second. All right, but there were some things on here that we need to talk about and work through that I was concerned about with the work. Still, again, even after our conversation yesterday, several people didn't upload the work, which kind of puzzles me.
It wasn't letting me upload it, like it wasn't.
Because it needs to be what type of file?
PDF. I was doing it as a PDF. I did it in my notes and everything, but it wasn't letting me for some reason do it. So what I did was I put it in the comment section for you. I don't know if you can open it up.
I graded them if I got them. I can't see stuff in the comment section. So more than likely, if you can't upload it, it's because it's not a PDF document. Okay. So we need to go in and look at it.
I have to pick right now if you can take it.
We need to make sure we check the scan though. That was the whole thing about that, right? I could put it in here. If it's in here, I can grade it quickly. It's all in here. It's not the first time we've uploaded something. So that's where I'm coming from with that. So keep that in mind. All right, so as we go through these problems here, all right, we need to review them because some people didn't set up the long division correctly, but we did not complete it correctly. Now, everything here was already present, descending orders. We didn't have to worry about other stuff as far as making sure we put the terms in their proper order. It was more about just remember putting it into a long division form. Now, make sure, again, that's what I told us to do here is use long division to divide, identify the quotient and the remainder. Okay. With that said, the thing that start this again today, huh? The thing that I did see on some people, though, is they were putting answers on there, but it's kind of hard for me to know where you got something from, right? So when people are making mistakes, I have a lot to kind of show where those mistakes came into play. So keep that in mind, right? Now, again, you do not have to show this off to the side. Just know that when I looked at it, there were a couple areas where I wasn't sure what happened, what went wrong. Is that clear to everyone? So as you write out your work, make sure you double check some things, right? So those of you who did turn in an ID see the X squared, but here's one thing that I was very straightforward about, right? Why did I put the X squared where I put it? It's above X squared, right? Now, some of you probably confused yourself when you were doing it because you didn't follow something as little as that, right? Like terms matter. Order and organization matter as far as how we write stuff. So it's important that we follow that. Okay. It's like if I came over here and I said, hey, 25 divided into 357, you wouldn't put the 1 right here. That wouldn't make sense. When we do that division, we start by saying 25 into 35, right? Which means the 1 must be right here. Well, guess what? We don't want to change that pattern. Okay, don't change that pattern. The nice thing about polynomials, we have something that tells us where to put it. Okay, now keep in mind, if you have a term missing, that's why I left a space, and I even encourage you to put +0, whatever it is. Okay. With that said, though, again, I never said you had to write this over here. This was just me showing the steps, right? But always double check your own work. The one thing that was confirmation that you probably did the right thing here was which part? The first term, right? What's nice about it though, right? Many of you found out not just the first one, but also the second one, right? So that gives us 0, 0, and then what, 9x squared? And this is where I started getting some mixed stuff, especially, right? And most of you that turned in your work, you had the x squared. So with that said, as we move forward, it's the same thing over again, right? But make sure you see here, we go right back to the same pattern that we had.
I wrote the question wrong.
Well, that's one thing we want to be careful of because that's going to make it probably more difficult to work with, right? This one here, I intentionally made it to where we had to do long division twice. Like you had to do long division because of the x squared, right? But I wanted it to be something where you had to go through the process twice. Not only that, I made sure that it had a remainder. Okay. So with that said, though, we have x squared plus 3 at 2x minus 5, right? Which one is the quotient? Right. Which I did see some of you put like cube x equals, which is, like I said, if you put the quotient is this, that's fine, but cube x is also another notation that I was using. And then our remainder, r of x, is the 2x minus 5. Now, like I said, one thing that I looked at is as far as the written work was concerned, some of y'all made an error, and it's hard for me to trace an error when there isn't kind of something to help show me where it came from, right? So you're going to lose more points that way. So keep that in mind to double check your work. It could have been just something as simple as distributing the 3 and you forgot to go to the 2, right? So always double check those little things. Overall, though, I think, like I said, most of y'all at least put it in this form, right? So that was a good start, okay? One concern that I saw in several places was make sure you see here the importance of placing things in a certain location. Right, I put this plus 3 way by itself because that's where all the constant terms are, right? So make sure you keep that consistency going. Anything I clear up with this one? All right, so here's one that I saw a lot of inconsistency on. Oops. And I would hope that a fraction doesn't cause that much of a breakdown. Okay. The key here was I told you to do synthetic division. Evaluate the function using synthetic division in the remainder theorem, right? So remember right away, write this. F of 1/2 equals whatever my remainder is. Remind yourself what the remainder theorem is. If you don't do F of 1/2, remember that in general, it's F of K equals R. The whole point of doing this is to get the remainder. That's why I give you the hint from the remainder theorem. And the number of you, most of you did not even give me this statement when you were done. Okay, so we have to make sure that. Now, all but one person did do the synthetic division. Some of y'all, though, started using decimals. I think you confuse yourself in that process. Okay, so we have to be careful. Now, with this said, we do have to deal with the fraction. But the nice thing is 1 times 1/2 is 1/2. Well, what's 1 plus 1/2? What, 1 and 1/2, right? Now, you can rewrite it as 2/2, though, right? Which would give you 3/2. I still, like I said, some of you put 1.5. So technically 1.5 is perfectly fine, but all I have to do is change this to 1/3, and all of a sudden now we can't use the decimal. So be careful, all right? But coming over here now, then we have 3/4 or 0.75, right? Now keep in mind that means you can change this to -8/4, because how many times does 4 go into 8? 2 times, right? And isn't that what we had was -2? So make sure you see there and use those things. That's nice about that. If you get stuck, go off to the side and write things the way that you remember to write them. All I did was multiply top and bottom by 4. But at the same time, have that confidence, say, hey, I know 4 goes into 8 2 times. That's why I'm allowed to change that, okay? But that gives us what, -5/4? Which then give us what, -5/8? All right, and the last one here, again, since it's 1, we can just make that -8/8. So that's where -13/8 come from. Which I don't, the decimal is what, 1 5/8. So it'd be like -1.625 maybe, like if I'm thinking correctly. Now, the problem here I had, though, is some of you had some right values here, or values that were going on the right path. So we just got to fix some things, right? The one thing I did not see consistently done here, though, is f of 1/2 equals what? The whole point of the problem was to evaluate the function. Now, like I said, everyone used synthetic division but one person. The one person didn't do synthetic division. As I mentioned, I wouldn't give any credit for the problem. I didn't say plug in the value to evaluate it. I was very specific that you should use synthetic division to do it. So if you plug in the value, yeah, you're evaluating the function. But this is what I was looking for you to check to see that you knew that, hey, whatever the remainder is what I would have gotten plugging it in. Okay. Now, it's not, we're not going to use fractions all the time. Make sure you go back and look at some of the other stuff we did. There are fractions possible, but we didn't have to use them most of the time, right? There are times where we're going to, but not all the time. So keep that in mind. Anything I could clear up with this one? Would you rather have this one on the quiz or on the test, though? I'll put it on the test then. No? You don't want this one on the test?
Yeah, we can.
Now, the reason I asked that, because that means some of us haven't looked at my practice test yet, right? Would you rather that or this?
Oh, yeah, never mind. That.
That one, right? Does it change what we did though? No, the key here is, remember, as you see, write that down first. Remind yourself that what you're trying to find is going to equal the remainder. Right? So that when you're done, this is one of those things that hopefully you're hearing me, that people skip on, that we talk about it, right? We use it all the time in everything we're doing here. And it's like the definitions on exam too. I use those terms every single day, intentionally knowing they were on the test. Right? So like for this class here, what's one of the terms we've talked about over the past 2 weeks a lot? We're working with polynomials. So if you look at this polynomial, what's something that should stand out to us? The leading term, leading coefficient, right? The constant term, right? These things start to tell us some things about the problem, right? Hey, like the degree, the leading coefficient helps us with whether or not there's reflection, right? So guess what? What is this term going to be considered when we look at this function? Even though we've never written like this, what would that term be considered? Right? I have it highlighted so it helps, but make sure you see here that, hey, there's no x on that one, so that's my constant term, so that must be my leading term. Okay. You taking a picture of my test?
No, yeah. Let me try that.
The practice test is on campus. Not, yeah, it should be on campus.
No, I really can't.
The same ones are on the test though. The same ones are on the practice test. That clear to everyone? The only difference there, I think it's a drop down box. Okay.
Trying to look at it.
I understand though, the test only difference is a drop down box, right? You click on it and you select from the drop down box. Okay. But like, as you deal with this, the y-intercept can be identified by the constant term, right? So the questions may be a little bit different than what we've used in class every single day, but it all centers around those same things, okay? Some of these other ones know that we're going to go into that kind of a little bit today with rational functions, all right? But I felt like after I looked at that quiz, it was important that we do kind of talk about this stuff. All right, so are we okay with where I'm coming from and the importance of making sure to put this when we're done? All right, now, hopefully you saw, did I do a fraction on the test? No, right? You'd rather have this on a quiz that's considered a low stakes assessment than a test, right? So keep that in mind. Now, the way I handled the quiz, though, is everyone got 70% for turning it in. So brain's not working. What am I doing? Okay. This last one, though, let's make sure we take the directions with us, because some people didn't read the directions here. All right, so this last one here, this is where reading the directions is very important. Now, I would say most of you did do at least one part correct, but some of you didn't read the directions at all. Okay. With that said, make sure again you see here, I'm saying use synthetic division and the remainder theorem, but this time I said to find a zero of the function, right? So what remainder do we want? That's what it means, right? We're trying to find when does this function equal 0. What I did appreciate is several of you did write the correct thing that we should start with, right? We don't want to just use any random numbers here, right? We need to focus on what are numbers that work with this problem specifically. And this is one of the things that is very helpful. I didn't tell you to write it, but writing out your possible rational zeros is definitely something you should want to do. Let's limit what we're working with. Well, that's where these two things come into play, right? The constant term, the leading coefficient, right? Since the leading coefficient is 1, we won't have any fractions, so that's nice. So it's just factors of 8. So we'd have what? Plus or minus 1, 2, 4, and squeeze it in there, an 8. So we good with where those values are coming from? Which, like I said, I think I saw it on a couple papers. I'm not going to say for sure who did or did not, but make sure you see here that even though it's not told you to do that, that's something you should want to do. There's an infinite number of values we can choose from. This brings it down to 8 different values I can use, right? So with that said, this is where the synthetic division comes in, which I think most sheets you had synthetic division on there. There was a couple of people that caught on to the fact that you could factor this. Now, with that said, is there anything wrong with factoring it to check your work? Not at all, right? So if you recognize you could factor, go off to the side and write that out. Like, hey, I know that I can factor this by grouping, so let's see what I get. With that said, if you did this first, how can you do this to help you with the synthetic division? What number does someone want to start with? You started with 2. All right. So 2 is perfectly fine. Make sure you see here, though, that we should know that 2 is already going to work if you recognize it's factorable, right? Like I said, I did see someone do this, but the problem is, if that's all you put on this problem, you didn't follow the directions. I wanted synthetic division here, right? So if I go through here and I'm going to go and put in the 2, and we're going to find that it does work. Because we get g of 2 equal to 0. All right. Now, here's the part that, again, there was some inconsistency. Well, how do I move forward? Well, remember here, what you just found is that x minus 2 is a factor of that function. That's what it means to be a 0, right? Of a polynomial function, it's a linear factor. With that in place, though, we still need to have something with x squared involved. That's where the quotient comes into play. So make sure we remind ourselves like, hey, if it starts at x cubed, then this needs to be x squared, x in constant term. So it'll give us x squared plus 4x plus 4. All right. Now, do these things look exactly the same? Huh? No, right? But guess what? Isn't that a difference of squares up here? Whereas down here, the factors of 4 that add to 4 multiply to 4 are positive 2 and positive 2, right? Aren't these exactly the same now? So you can see then at that point that, hey, I need to do this because this was the directions, right? Just following directions. I did this approach here. However, I could do this to make sure that I follow and get to the same place.
Does it matter if you like instead of putting g of 2, can we put h of 2? Like, I know that like whenever you do it, like does it matter what we put in front of that?
Yeah, because that's going back to this.
Okay, so it does matter.
Mm-hmm. Yeah, we should be in agreeing with whatever function we're working with at that time, which is why I tried to vary the letters I use. Some of you might have caught that on exam too. I try to do different letters for every function on the test so there wasn't mixing up by mistake. Okay. Now, with that said, though, make sure you see here, I wanted you to find the zeros and their multiplicity. So hopefully you kind of follow that little chart approach. You don't have to write it out this way. Just make sure you have a clear way for me to see the 0 and the multiplicity that goes with that 0, okay? So we would have negative 2 and positive 2. And the multiplicity for the negative 2 is 2 factors, right? And then the multiplicity of the positive 2 is only 1 factor. But again, make sure you see here 2 plus 1 goes back to our degree of 3. So we're good. Now, if all I said was to graph this function and you were trying to find the x-intercepts on your own, does it matter which way you choose to do it? No, right? The problem with this one, I intentionally made it you use synthetic division. Okay. But I did see a couple people saw that you could factor by grouping, and that's fine. Just make sure, again, go back and use the directed statement to complete the problem. That would be the main thing there. Okay. Is there anything unclear up here? With that said, then I will extend the due date to tonight at 11. Upload a new file with the corrections, and you'll get 100% on the quiz. It does have to be a PDF file. So if you need to know how to look up and get a PDF file, make sure you check the file you're trying to upload for one, but go through Google to learn how to do it. If you're using an iPhone, just go to your Notes app, create a new note, hit the camera and hit Scan Document. If you updated already, hit the paperclip and then hit Scan Document. Just make sure you save it to your files, because once you save it to your files, that's where it's going to become the PDF file that you can access. If you have an Android, I recommend Adobe Scan. Adobe Scan can be used on the iPhone too. For whatever reason, iPhone users are very discriminatory when it comes to using things. So, any questions? What did I say about this quiz before I finish and move forward? Well, hopefully you took notes right now, right? What just happened? Hopefully you took notes just now, right? Because I should see people turning in the correction, right? So hopefully we all have the correct statement there. Okay. There should be no excuse for not turning in a correct paper. All right. Now, hopefully what you heard though is I talked about the ones that I did see. I felt people made honest attempts on some of them, right? Even if you looked at your notes, I didn't say don't use your notes. It was a take-home quiz, right? There's just some things that we needed to clean up as we prepare for the test. With that said too, go take the practice test. You may not be able to do all the problems as we just saw with the vocabulary stuff, right? There's a couple things that we're going to start talking about from the rational side. But at this point, go take that practice test and focus on all the polynomial problems to make sure we're comfortable with them. All right. Huh? Yeah, you can have a note card. What? All right, so if we have time, I'll do another polynomial though to make sure we are comfortable with that, but I want to make sure we do introduce some new. It's not necessarily new. We're going to go more detail. Let me picture, because like polynomials, graphing and stuff wasn't new. We were just able to go into more detail. That's the key. Make sure you see though, we were still limited on how much we can do. Something is like finding the minimum, the maximum values of a graph. Really a quadratic or absolute value are the only ones we can do that with. So we have to make sure to see how that applies in other situations. So the next step is for us to go into rational functions. Rational functions work with polynomial functions because we're going to talk about it from a definition standpoint, because to have a rational function, you need polynomial functions. Okay. With that said, though, if you're given a function at this point, we should be able to get the domain. What is the domain of this quadratic function? All right, all real numbers. Anytime you see polynomial, linear, it's all real numbers. What is the domain of a rational function? What's the issue? What's the restriction for rational functions? The denominator can't be zero, right? We can't divide by zero. That's our restriction. So understand, we can use all real numbers, but in this case, we can't use what? 2. Remember, that's the domain. All real numbers, just not 2. Is that clear to everyone? Now, as some of you are trying to remember those, we use interval notation, right? Interval notation highlights that we're saying, hey, all real numbers, but I write the 2 twice, because what symbol am I putting with the 2's? But before I get the union, make sure I put parentheses on both of them, right? Parenthesis means don't use those. It's what we call an open interval. I can't include that endpoint. It's not usable. The union symbol is important though, because it's saying, hey, this is one thing. Even though I wrote 2 separate pieces, it's still one domain. Okay. Every number less than 2, every number greater than 2. I can use all of those. But in the end, please remember the main point of this is do not use 2. Because that would give us 0 in the denominator. And that's not something that's defined mathematically. We can't do it. With that said, though, moving forward, here's some other functions we haven't seen in a while, so I want to make sure to review those. What's the domain of a cube root function?
Would it be negative infinity to infinity because like the cube is like a
So you're saying since the cube looks like this, the cube root will look something like this?
never mind. This is
But is it?
I don't know.
What can we use to help us here? I don't think you're wrong. Oops. Yeah, I'm going to use the graph because there's something here that you can key on though, right? You're saying we can compare it to a cubing function, right? The cube by itself, just x cubed looks like this, right? From an inverse standpoint, right? If I give you y equals x cubed and we invert that, we get x equals y cubed. Doesn't the cube root solve for y? So we would have y equals the cube root of x. So they have a special relationship, right? Just remember from inverse standpoint, why am I drawing this? What was special about this line? Go straight through the origin, right? So y equals x, right? Remember, if I do f of g of x and g of f of x, and I get x for both of those, that's how we were able to determine that something was an inverse of one another, right? Well, that's where we also see this reflection come in, that I could draw this now. If I could draw it well. To where that cube root does have, what in the world happened? Technology has not been my friend this week, y'all. But I could draw in that second green line here, which shows that, hey, the cube root does have a similarity to a x cube function, right? Which means that you can conclude that this one would have a domain of all real numbers. Okay. Now, keep in mind, that's just for this situation. There's only one x in there. I could graph this one using transformations if I wanted to, because it's just x minus 2 inside. If we had something else involved, we'd have to be careful. Make sure you see that, like when we look at polynomials, right, that got a little bit more involved because of some of the stuff that we added to the problem, okay? But just kind of based on that, like if you look at it from the perspective of an inverse, we can be like, okay, cube root of x, we can safely say all real numbers. All right, now be careful anytime you bring in a cube root, x cubed, there are some similarity or some issues that could come up. But in this situation, we're fine. What's the difference with j of x? What type of function is j of x? The square root, right? And what is it that about square roots we have to be careful of? Right. Why are negatives something we have to be careful with square roots? They give us imaginary. Do we want imaginary right now? Is there anything wrong with imaginary? No, but we've been focused on real numbers, right? So make sure you see here that we have to then say, hey, there's a restriction here where 6 minus x better be greater than or equal to 0. Well, now that's an inequality. That is my interval. I just got to go do what? Got to get x by itself, right? So what would someone do here to get x by itself? Y 12.
Wait, you said get away.
We're trying to get x by itself here.
Oh. Oh, I was reading the problem.
Yeah, no, remember, we're focused on the domain.
-6.
You can definitely do that. You're making it harder on yourself though.
Uh,
I would add an x to both sides. If you choose to add this or subtract the 6 from both sides, you'll be fine. Just remember, the second that you divide by -6 on both sides, you have to change the inequality symbol. Yeah. I have no clue. There we go. Is it Thanksgiving yet? Make sure you see here that either way you get the same solution set. They both are saying x better be less than or equal to 6. With that said, then, hey, I can use any number, including 6, right? As long as it's less than 6. So the interval we would use here would be -infinity up to the 6 with a bracket. Now, make sure that you see that the limitation that we're dealing with comes from that idea that, hey, if I try to plug in 7, I'm going to get an imaginary value, right? If we had all the tools in place and that's what we're focused on, we could deal with that, right? So if you like that kind of stuff, like I said, start signing up for more math classes. You can see how it gets used. But for our focus, we wanted to focus on the real numbers, right? So that's where we do stuff like, hey, this is our focus, all real numbers, okay? Any questions with where I'm getting these domains from? All right, the one thing I would highlight then is, remember, whenever you see functions, these are the two situations that you need to watch for at the moment. After we take test 3, there'll be another function that we introduce that has a restriction involved, but these are the two that we're focused on. If I see rational, the denominator cannot be 0. If I see a square root, I don't want negatives. I don't want complex numbers right now. So let me make sure I limit to what I'm working with. Okay. Any questions? Make sure we're practicing naming stuff then, right? Cube root, square root. Go back to your first test and review all that so you make sure you remember some of those things, okay? Now, what we need to do, though, is set some things in place, right? So here's some new notation, all right? What we're looking at right now is going to be a we're dealing with a rational function, right? Now, what happens is a rational function is made up of a numerator and a denominator. So that's why I'm using n of x and d of x. What you're going to find, though, is these are functions themselves that are both polynomial. So make sure you understand that as we deal with this, we're going to have a polynomial divided by a polynomial. That's what makes something rational. All right. The n of x stands for the numerator. That means it's up top. The d of x stands for the denominator. And that's why it's in the bottom. Okay. With that said, because we know it's a polynomial, right, there's some things that we can take with us that are nice, right? So if I'm trying to find the y-intercept of my rational function, that means I'm plugging 0 into every x value, right? But if you have a polynomial, what term do you get back whenever you plug in 0? Well, if I don't know the polynomial, what term do we know we know for sure we'll get back this particular term? We're trying to find the y-intercept. So if I go look at a polynomial and I plug in 0 into that polynomial, what's left? If I plug 0 into this polynomial, what's left? All this goes away. You'll always be left with the constant term, right? So make sure you understand that as you deal with this, for a rational function, we can take that with us, right? It's just a polynomial over polynomial, so it's going to be whatever your constant term of n is. right, over the constant term of d. So whatever the constant term in the numerator over whatever the constant term in the denominator is, and that'll be your y-intercept. Now keep in mind, not every function is going to have a y-intercept because we cannot divide by 0. So we have to always keep that in mind. Okay. With that said, the next step then is to go find the x-intercepts. So make sure you're writing here that this is going to represent your y-intercept. This will be our x-intercept. So I'm taking the function and I'm setting it equal to 0. So this is again also known as the zeros of the function. Now, the nice thing about this is I'm taking that thing we talked about at the top and I'm setting it equal to 0, right? Well, remember, use multiplication to eliminate fractions. What is 0 times anything? 0, right? So understand as we deal with that, your zeros of your rational function will come from which part of it? So as I look at this rational function, right, that's written in this form, I set the whole function equal to 0. What part of the function will actually have the x-intercepts, if any? What letter do we see here? What does the n stand for? The numerator, right? So that the top part of our function is where we find x-intercepts. What does the bottom function do for us? Right? Well, remember, the bottom part of our function is very important. We would put comma, the denominator cannot be what? 0. So the numerator can be 0, and that will represent x-intercepts, while the denominator cannot be 0. That represents our restrictions. Okay. Now, what we're going to find here as we deal with rationals, we need to start defining those restrictions. What's happening as we look at them. Okay. Now, with that said, make sure you see here, though, again, that we are able to find x-intercepts and y-intercepts just like we did before by plugging in 0 or setting it equal to 0. Make sure you keep these things in mind, though. Don't overwork yourself if you already know the numerator is the only thing that's going to be left. Now, that's only true, though, if it equals 0. So keep that in mind as well. All right. Now, let's look at a practical application of this. Okay. Now, here's one where we could have done transformations. Make sure you see here, it would be a horizontal shift to the left 5. And then that 2 would be considered a vertical stretch. All right, that 2 would be a stretch. So we could have used transformations, but let's use what we've talked about as far as finding things to work with. All right. So the nice thing about these polynomial situations, the top part is just a constant function 2, and the bottom is a linear x plus 5, right? So dealing with those isn't going to be too bad. So we could actually jump in then and start finding some points to work with, right? So let's look at f of 0. That would give us 2 all over 0 plus 5. So I do have a y-intercept, probably about right here somewhere, right? No, I did these by halves. Make sure you see that's halves. 2/5 will be more like right here. My graph is by halves, so make sure you catch that. Okay. Now, what did I plug in to get that first point? All right. We're letting x equals 0 so that we can find our y-intercept, right? So make sure we're going back over the things we did before. The next step here then would be like, hey, let's go find our x-intercepts. Not that I have any, but let's go look and see. You're not always going to have x-intercepts, right? So that's one thing to be aware of. It's like, remember some of the quadratics we looked at didn't cross the x-axis, all right? The same thing could happen with any even polynomial. I can give you an x to the 6th that does one of these where it never touches the x-axis, right? That wouldn't be fun to work with because guess what? You would do all that synthetic division and you wouldn't find a single number that works. So we didn't run into those, okay? What you'll find there is, again, that's where something like, say, dealing with calculus would help us a lot, okay? We're not going that far though, right? We focused on intercepts. With that said though, what part of this fraction becomes our focus? when I'm trying to find the x-intercepts? Remember the x plus 5, we should have came up here and said this, right? So what we see here is this implies that 2 equals 0, which is that true or false? Does 2 equal 0? No, so you would say false, no x-intercepts. Okay, the x plus 5 is important, but that's our restriction. We do not want to use the -5. Okay, so make sure we catch on to that there, because that's going to be an important part. With that said, then we need to make sure to shift this over some so that our focus becomes on this next part, right? Because all we got out of that was one point, which was the y-intercepts. Did that help us a lot? Not really, but hey, that's what we know to start with. All right, so I'm going to go over here. All right, so I added some more stuff over here. What we're going to find here, if you remember, we kind of briefly talked about this. And when I say briefly, didn't go a long time into it. We talked about the fact that when you have a rational function and you have a restricted value, right, what we want to look at that as is possibly what we call a vertical asymptote. Now, what I kind of talked about that for is I'm putting that dotted line there to say I cannot plug that in, right? That's going to affect my graph in some kind of way. Okay. Now, where we're at right now, the best we can do is just start plugging in points, because all we got was that one y-intercept, and that's kind of out of the way. That's nowhere near this asymptote, right? So what we want to focus on right now is saying, hey, since I don't have much to go with, let's just start building a table and see what happens when I start plugging in values. Now, I will say that this is going to be one of those places where we're doing our best to sketch a graph. We're not going into full details. Is that clear to everyone? But there's going to be two things that do help us with rationals. The first one, as you can see here, is focusing on restrictions. The restrictions is one aspect that's going to help us. Now, as far as plugging in values, I'm going to plug in some numbers that look like this. I'm going to plug in -7, -6, -5.5, or -11/2, right? I'm putting it as -11/2, but I'm focusing on this value here. Okay. And then on the other side, I'm going to do -4.5, so 4.5, so -9/2, -4, and -3. So these here are kind of like, hey, 2 on the left and 2 on the right of my -5. But because I'm working with a fraction, I'm going to bring in a rational, I'm going to bring in some fractions where we focus on right next to the what I'm going to call an asymptote here in a second. Okay. So as close as we can. And technically speaking, we should keep getting closer and closer as best as we're able to.
It's supposed to be 1, like not.
No, it's supposed to be 9/2. I said 9/2. I don't know. It's turning one of those days as far as my brain apparently. All right, so this is one thing I will say. This is where your calculator is going to help you out a lot. Okay. So make sure we're comfortable with your calculator. Now, I learned something really cool yesterday. If you go to your calculator, if you have that TI-30X2S that you have, there's a great way to evaluate functions that I literally learned yesterday. Something I didn't know you can do. So in your TI-30 calculator, what you want to do is put 2 divided by a parenthesis, and then find your A and S key. So you're going to put that answer key here, followed by the +5. Yep, I think it's down by the equal sign. Is it there? You have to hit second in the equal sign, maybe?
Yeah.
Make sure you see here, though, this is what you should be seeing is 2 divided by answer +5. What's around the answer +5, though? Hit equals. Now, once that's in place, don't hit clear or anything. hit -7. It's gonna erase everything there, so type -7 and hit equals. And your calculator should tell you -7, right? Now click back, hit the up arrow back to this statement. Hit equals. Should we have -1? What's -7 plus 5? If you owe someone $7 and you give them $5, how much is left over? You still owe them 2, right? And then 2 divided by 2 is 1, right? So it's supposed to be -1, right? Well, guess what? Go put -6 in your calculator, hit equals, and go back up to this statement again and hit equals. And you should get what? Did you get -2? What happened?
I don't know. It's not happening.
Do you still have that in your calculator? Did you clear it out?
Yeah.
All right, start by typing -7 and hit equals. -6, sorry, -6, hit equals. Because your calculator only showed -6 on the screen now. Now click the up arrow back to this statement here. Right, now hit equals again.
I got 0.18.
What do you have?
I don't know.
Bring it here, let me see. What are you doing? Did you get it? What are y'all doing? So we have 2 divided by parentheses, second answer plus 5, right? Equals random. -6 equals, all we have is -6. I
You said
clicked,
6.
I said -6.
You said 6.
Look at the screen. Oh, it's supposed to be -6.
That was it. You said it.
Well, go what I wrote, not what I said. Well, this time anyways. Does everyone else get -2 though?
Yeah, got it.
Now, the reason this is nice is technically speaking, we should be comfortable with the integers, right? Hopefully you catch on the integers work out nicely.
How do you do fractions in here?
Do the division symbol, -11 divided by 2.
Like, how you do that? Oh, you're so smart.
Apparently, if you need help with fractions, come up here right now so you can see what's going on.
I'm gonna write that down.
All right. Now, I filled in the other ones, right? But make sure you're comfortable with your calculator. Okay. The nice thing is the values I chose all came out to integer values when I plugged them in, right? So it may not have looked nice. Okay. Technically speaking, we should still be able to do that by hand, but hopefully you find a nice way to use your calculator. That, like I said, I learned that yesterday. I didn't know you can do that in there. I knew about the answer key. I just didn't know you can go back and use that multiple times. That's pretty cool if you ask me. With that said, though, when I start plotting these new points, we have an interesting issue that we have to talk about. All right. What do you notice about the points when we consider the fact that we're trying to connect the dots at this point, at this step? Do they form a nice curve that we can use to help us graph this? What do you notice about all of these points here? They're all what though? What type of values? They're all above the x-axis, right? Where these are all below the x-axis. Should I take this point and connect it to that point? Why not? But we don't want to use -5, right? So if we just follow that, the fact that we don't want to use -5, what you need to do is kind of draw a line that looks like this. All right. Now, if you wanted to, you could do something like negative 5.0001. What you're going to get is a very negative value that confirms that we should be going downwards. If you do negative 4.9999, you're going to get a value that's really big, that's positive, that confirms this. The key here to understand is if these two lines are going in the opposite direction, will they ever meet? No. Well, if these two lines are going in the opposite direction, will they ever meet? No, right? So what we see here is that as we deal with rational functions, we're dealing with graphs that now are going to have more than one part to the graph possibly. And this is where we come in and talk about what we call asymptotes, okay? By definition of an asymptote, what you're seeing here is you have a graph that's been broken up because of a value that we cannot use. One side of this asymptote is going to negative infinity. The other side of the asymptote is going up to positive infinity, right? So there's no agreement there, right? And this goes back to why we can't divide by 0, right? Because if I try to do 1 divided by -1, I get -1. You do 1 divided by itself, you get +1. They're moving in the opposite direction, okay? With that said, though, don't these two behave kind of in a similar way that we're seeing these two ends, though? Because what you're going to find here is we deal with rational functions. Not only are we going to deal with vertical asymptotes, we're also going to deal with horizontal asymptotes, okay? Now, the one thing I will say about this, when you look at this, make sure we're getting comfortable with this idea of an asymptote, because the asymptote's going to affect my graph. So like this would be the vertical asymptote at x equals -5. This is a horizontal asymptote at y equals 0. They affect our graph. The vertical asymptote, we will never touch or cross. It represents a value that I could not plug in because it puts 0 in the denominator, okay? So make sure you remember that, and that's where we see here, again, my two lines can never get to each other, going in opposite directions. The horizontal asymptote represents end behavior. What you're going to find is as we deal with other types of rational functions, that's not always going to be horizontal. It could be slant, it can be oblique. There's different things that we can do there, okay? So understand that right now, it's the way it is because of the problem I chose to use. All right. Now, what that means is in order to graph a rational, we need to find these things. So as we talked about polynomials being able to find the end behavior and the zeros to help us graph it, for rationals, we need to find the restrictions, right? And define what those restrictions are doing, and then the end behavior as well. Now, keep in mind, as the end behavior here, what we would say, as we did previously, is like, hey, as x approaches negative infinity or the left-hand side, make sure you see here, this is that left-hand side and this is the right-hand side, that we're going to approach a particular value. So we would say, and I should use f, sorry. We would say, hey, f approaches 0. The big difference here, remember, polynomials, we used infinity, right? To see, hey, it either rises or falls. Positive infinity rise, negative infinity falls. The big difference here is I'm approaching 0. Now, will I ever get to 0? Okay, how many of you have that statement still in your calculator? Go plug in 2,000 for me. So if I take what we're working with here and I plug in 2,000, what happens? What is 2 divided by 2005? I guess would be another one. A great year.
The positive 2000?
Positive 2. Well, it doesn't matter. You could do negative 2000 as well. Both of them will show us something important here. Okay. Because as I've told you, the vertical asymptote we'll never touch or cross, right? There's no way we can use -5 here. We're not allowed to. But we also need to see that that horizontal one sometimes have similar things that go on. But this, again, makes you see, I said the horizontal is in behavior. It affects the graph like a magnet in a sense, pulling it to that. If you plug it in, you should get something like 9.975 times 10 to the -4. Just do in your calculator 2 divided by 2005.
Is it two?
2 divided by 2005. The reason I want you to see that is that times 10 to the negative 4 means that number is really big or really small? Really small. Well, if it's getting really, really small, what is it approaching? It's approaching 0, right? Now, guess what? If you take 2,000 and change that now to, say, 2 million, do you think you're going to get 0? If I change it to 2 million, I get 9.999975 times 10 to the negative 7. Is that 0? No. However, if we rounded that, what would we put? Right? Depending on your perspective, right? You can see that at some point is going to be indistinguishable from 0. It's just so small. So keep that in mind. Any questions with that? Just kind of a quick overview of some of the things that we're going to do with rationals here. All right, let's look at another one then. Now this one's going to be similar, but what I want to just notice is that I changed up that denominator a little bit, so we have to be careful with that. Now, if we follow kind of some of the stuff we dealt with, right, we need to start identifying things. Now, with rationals, I technically say we should go identify restrictions first. That doesn't mean we're going to have any again. That's just something we need to look for. So what is it that we got to be careful not to use here? What is it that we're saying can't be 0 is the key. But the denominator, right? X squared minus 4 cannot be 0, right? And how would someone solve that?
Plus 4.
That's perfectly fine as long as you remember to put what? Plus or minus, right? So X cannot be plus or minus 2. So how many restrictions did I get? 2, right? Is that okay to have 2 restrictions? Absolutely, right? But just know right here, the thing that you want to look at is now go up here and try to factor it. You will need your factoring skills. Factoring skills will be a must when it comes to dealing with rationals. If you do not know how to factor something at this point, we're in trouble. It needs to be fixed. All right, which is why I started week 1 basically when it came to factoring. Okay, so make sure you see here, you should be able to solve it this way, but no, factoring is another great way to solve it. With that said though, the factors in the denominator, do they match the numerator at all? Is there any factoring common at all in this problem? All right, so I can't simplify anything, right? It's just, I got to deal with it as it is, okay? Now, what that means is the way that I'll interpret this, since I cannot simplify anything, both of these zeros here are going to be vertical asymptotes. All right, so that means the first thing I want to do for my graph is go plot out both of these as vertical asymptotes. Now, why are vertical asymptotes important? Remember, we can never touch nor cross these. And that comes from that denominator not being equal to 0. Okay, are those red lines actually part of my graph? No, right? We're just putting them there to say, hey, don't use them, which is why I'm using a dotted line too. I would encourage you to use dotted lines when you're drawing these by hands. Make sure to show this is not a part of my graph, but it has a big impact on what I'm dealing with here. Now that I have my restrictions in place, okay, and no, that means I'm going to have something in each section, right? That's what the domain says is, hey, all real numbers, just not those values. So the way we interpret the domain here is make sure I graph something in all 3 of those areas, okay? My next step though is to go find intercepts, right? So what terms do I use again if I'm trying to find the y-intercept? The constant terms, right? But make sure you see here, you have 2 of them now, right? You have the numerator and the denominator, which means guess what? I still have a fraction here again, right? 1/4. So that'll be about right here. And make sure you see again, I'm counting by every other one here again. Now that gives me my one y-intercept I should have, right? So what should I go look for next? My x-intercepts, right? Which is setting the whole thing equal to 0. Just remember here though, that you only want the numerator. What has been going on, y'all? We only want the numerator. So we're going to say, hey, 2x minus 1 equals 0. Okay, remember, as I showed you, you just multiply both sides by the denominator. It's gone. Now, keep in mind, it's just a fraction by itself. Okay, if you had other terms, you have to be careful with how you handle that. This is just one fraction equal to 0. So that's why we're allowed to do that. So that means, hey, I will have an x-intercept this time, right? At x equal to 1/2. Which really doesn't help us at all. Okay, so the next best step is to just start plugging in points. Now, keep in mind the points that I recommend plugging in are going to be there. Now, overall, what we're going to talk about as we move through this, you can kind of look at the multiplicity of something and know something is going to happen. But right now, we're just kind of, what's the main idea? So let's plug in these points and look it out. So someone get out your calculator and do the 4, 3 and yell it out when you get those. Hopefully you're doing what I just showed you, right? 2 times answer minus 1. Make sure you put parentheses now, of course. If you're doing this in your calculator, that TI 30x2s, parentheses 2 times the answer minus 1 divided by answer squared minus 4, and then close your parentheses. And then remember, after you hit equals, it might show a value. Just go in then and put 4 equals to the up sign back to that statement and hit equals again. Anybody got anything for that positive 4 yet? No one's helping me out, huh? Well, keep in mind, this was a chance to make sure you're comfortable with it in class when we can ask questions and such. So
for the -4, you got 0.75 or negative.
yeah, I think that's what I got. Yeah, negative 0.75. No, these are not as nice. So keep in mind, my points, like I think this one here was negative, what's that, 4/3? Right? So understand that these aren't necessarily coming out nicely, but this helps me see something, right? That as I draw this over here, I'm going to do this. Okay. Now, the one thing I haven't added yet is that horizontal part, right? What was that going to look like we saw the last one. So I'm going to wait till we get all these points in place first, though. Oops. What? Now, keep in mind though, as I said, all I'm doing is plugging in these values. As such. Now, hopefully you see here, these points, they follow kind of a similar pattern that we saw before. Where like, hey, these are definitely not going towards each other. Now, what happens is it does get a little bit more complicated because we have that middle part. Now, what you're going to see here, though, as I was saying, I was waiting till here to do, we're still going to have that horizontal part, and we'll talk about that more as we go through rationals, where we'll say like, hey, there's a horizontal asymptote at y equals 0. So that we can confidently know that, hey, this graph here will continue to approach 0, but never get there. The difference is here, make sure you see we have an x-intercept, right? Because we have an x-intercept, when I draw my graph, I will actually cross the x-axis, but that's okay because it's a horizontal asymptote. It's not a vertical asymptote. Vertical asymptotes are the ones you can never touch or cross. Horizontal, some things that you'll see here is, like I said, the flattening out of the graph. Why did that disappear? On the edges of the graph. The horizontal asymptote is more about in behavior. You also see kind of here, it flattens out a little bit as it approaches the intercept as well, right? There's things that it can do to the graph, but our main focus is in behavior there, okay? Now, make sure you see here, where did I get all these points from? All right, I just plugged in those values around the asymptotes. I plugged in these whole numbers right next to my asymptote here. I plugged in these whole numbers right next to my asymptote here. I also used the half values to make sure I got as close as possible with something as easy to work with as I could. But again, this is where your calculator skills will help you out a lot. Okay, your calculator skills will help you out a lot with getting some of these points. With that said, is my graph a perfect graph still? No, it's still more of a sketch. I just got a general idea. But make sure you see here, do these two things go the same direction? No. Do these two things go the same direction? No, right? Well, guess what? How many times did you see each of these factors occur? One time, right? So that'd be something to keep an eye on as we move forward. Now, some things I want you to take from today as we deal with this, the impact our restrictions have on our graphs. That's why we call them vertical asymptotes. Okay, so as you look at that graph and you look at this graph, make sure you see that impact that restriction had on the graph. The other thing is that rational functions have end behavior, just like we saw with polynomials. Okay. Now keep in mind that this represents division, so that's where the division is going to come into play with rationals, is talking about the end behavior. Okay, so we'll keep that in mind as well. Any questions or concerns that I could help clear up, like where I'm getting these values from and how I'm showing that they impact the graph? All right, make sure you see here, I went and just plugged stuff in using my calculator to show that we can confidently say this is happening. That's where the calculator came in. That's why I said plug in 2000 on this one, so you can see it's still positive. It just gets closer and closer to 0. The same thing's happening with that. Okay. Make sure you see here, we still have intercepts that we're going to find. That would be the other thing. Any questions as we finish up? All right, well, that's all we have time for today. Know that this is what we're continuing with as we move forward into tomorrow. So have a good day, and I'll see you tomorrow.